Hello friends, welcome to my channel. In this video, we are going to discuss about Opamp basics. This is just a quick reference for engineering graduates or practicing engineers to select an Opamp. In this video, we are going to cover what is an ideal characteristics of an Opamp, what are real characteristics of an Opamp, basic applications of Opamp, popular manufacturers, and few frequently asked queries. By definition, Opamp is a DC coupled high gain electronic voltage amplifier with a differential input. These are the common parameters that we need to consider to select an Opamp. They are common mode rejection ratio that will be infinite, ideally it is infinite, input impedance ideally infinite, output impedance ideally zero, open loop gain ideally infinite, power supply noise rejection ratio ideally infinite, input offset voltage ideally zero, bandwidth ideally infinite with a zero phase shift and with a infinite slew rate. In reality, these characteristics are mentioned in the following slides. Example, common mode rejection ratio. A perfect op-amp amplifies only the voltage difference between its two inputs complete inputs, completely rejecting all the voltages that are common to both. However, the differential input stage of a op amp is never perfect, leading to the amplification of these common voltages to some degree. The standard measure of this defect is called common mode rejection ratio. Generally, you can see in datasheet in dBs. And similarly, power supply rejection ratio, another parameter. The output of perfect amplifier will be completely independent from its power supply. Every real op-amp has a finite power supply rejection ratio that reflects how well the op-amp can reject the changes in its supply voltage. Right? This is also you can see in the datasheet as a dBs. Another parameter, finite bandwidth. All the amplifiers have a finite bandwidth, but in datasheet you can see it is linked with the gain bandwidth product. That's how they will mention. Let's go to the another parameter. Open loop gain is infinite in idle op amp, but finite in real applications, real op amps. Typically, it exhibits open loop DC gain above 1 lakh. Finite input. Another parameter is a input impedance. It is a it is also finite input impedance. MOSFETs input op amps often have a protection circuit that effectively short circuit any input differences greater than a small threshold. So the input impedance can appear to be very low in some tests. However, as long as these op amps are used in a typical high gain negative feedback application, these protection circuits will be inactive. The input bias and leakage current described below are more important design parameters for a typical op amp applications. Right? So let's go to the another parameter, um, output impedance, that is also non-zero in reality. The output impedance of an op-amp, ideal op-amp, is zero. This means regardless of the amount of the current drawn by the external load, the output voltage of the op-amp remains unaffected. That is no loading occurs. But in case of practical op-amp, there is some amount of output impedance. The ideal output voltage is divided between its internal resistance and any external external load resistances. Generally, this is undesired effect, so we prefer op-amps to have a very low output impedance. Higher the output resistance, the quiescent current drawn by the op-amp is also high. Right? Let's go to the another parameter, input bias current. This is also finite in real application. Due to the biasing requirements or leakage, a small amount of current typically in nanoampere and picoamperes flows through the inputs. When larger resistors or sources with a high output impedances are used in the circuit, these small currents can produce a large unmodeled voltage drops. If the input currents are matched and the impedances are looking out, both the inputs are matched, then the voltage produced at each input will be equal. Because of the op-amp operates on a difference between inputs, these matched voltages will have no effect. It is more common for input currents to be slightly mismatched. The difference is called the input offset current, and even with the matched resistances, a small offset voltage can be produced. This offset can create offsets and drifts in the op-amp, right? So this is also one of the critical parameter. And another one, input offset voltage. The input offset voltage is defined as a voltage that must be applied between the two terminals of an op-amp to obtain a 0 volts at the output. Ideally, output of an op-amp should be 0 volts when the inputs are grounded. In reality, input terminals are slightly different uh, DC potentials. Right? That is about ideal and non-ideal characteristics of an op-amp. So let's go to basic applications of an op-amp. So I have mentioned a few examples here for reference. The popular examples, non-inverting amplifier. So the circuit is mentioned as mentioned in the slide. Gain is 1 plus RF by Rin. Uh, Similarly, inverting amplifier. Here also input is connecting to the inverting terminal. So the gain is minus RF by Rin. That negative sign indicates voltage will be inverted when it comes to output. Another example, summing amplifier or adder. So this is a similar circuit to non-inverting current amplifier. So, but what happened? Two inputs are has come, so two inputs are added in the formula. In case if you add one more input, it will be added in the formula, right? Similarly, differential amplifier. So this is also called a subtractor. Only two inputs that we can connect through this circuit, and that the subtraction of the voltage input voltages, it will amplify and it will result as a output. So in majority of the applications, that R1 and R2 are equal, RF and RG are also equal. So in that case, simplified formula will be minus RF by R1 into V2 minus V1. But I just mentioned, in case the values are not equal due to some reasons, we can use below formula to calculate the output voltage. Another example is a integrator. This integrator is a simple RC circuit, high pass filter, sorry, low pass filter. So that's why its formula is output equal to minus 1 by RC into integration of input voltage. Similarly, differentiator circuit, like a high pass circuit, minus RC into differentiation of input voltage. Instrumentation amplifier. This instrumentation amplifier, if you notice, it is a combination of two non-inverting amplifiers. Uh, their inputs are V1 and V2, and one, you can see here, one differentiator, two non-inverting amplifiers, and one differential amplifier, right? So basically, these different instrumentation amplifiers will be used where high gain is needed, um, especially in case of pressure sensors, you know, uh, where the input voltage, sensing voltage is in terms of millivolt or microvolt. In those applications, this instrumentation amplifiers are used. Of course, it is costlier. So, but it will be definitely better than differential amplifier. It will give a better results. So that's why differential instrumentation amplifier is used. And another one, unity gain Opamp. This is a popular one. So input equal to output. Input equal is connecting to the non-inverting terminal. Just for isolation purpose, this unity gain Opamps are used. Another example, positive feedback configuration of an Opamp, or this is also called as a comparator. Simple. Um, in all the previous applications, if you notice, right, feedback resistor or feedback component is connected to negative non-inverting terminal, inverting terminal. But in this case, the feedback resistor will be connecting to the positive terminal or non-inverting terminal. Uh, so this is how the circuit looks like. Here, hysteresis to be designed to overcome the output chattering. Example, if we as it is use the circuit what I have mentioned, it will result a chattering output. You need to find a feedback resistor. Um, it is a challenge for the designer to select the hysteresis value to meet uh, its input requirement. All right. So uh, the how this will operate is, you can see here output equal to, if V input is greater than V output, it will result positive supply voltage. If V input a plus terminal voltage at plus terminal is less than the voltage at negative terminal, it will result um, negative supply. Right now it is connected to 0 volt, so I have mentioned it may result as a 0 volt. So these are popularly used in ADCs and DAC applications. Apart from the above mentioned general examples, these op-amps are popularly used in active analog filter applications. That is low pass filter, that can be low pass filter, high pass filter, band pass filter, or band reject filter. And again, each filter has five realizations: Butterworth response, Bessel response, Chebyshev response, inverse Chebyshev response, elliptical response. Elliptical is also called as a Carr filter. So based on your need uh, about filter realization, these op amps will be used. So these are the popular manufacturers: Texas Instruments, Analog Devices, Maxim Integrated, and Microchip Technology. Okay, let's go to few questions, frequently asked questions. That is, sometimes people may ask, what is a single-ended op amp? Input is applied at only one terminal, either inverting or non-inverting. Another terminal is connected to ground. What is, and another question, what is a single supply op amp and a dual supply op amp? Single supply op amps can operate just with a one supply voltage with reference to ground. Dual supply op amps need two supplies, plus VCC and minus VCC. And another question, what are rail-to-rail op-amps? Op-amps that are used to completely span between a negative and positive supply voltages for a signal conditioning applications. So these are the special op-amps. We can ask the manufacturer, or we can go through the manufacturer data, website. We can get it. Of course, they are costlier. So that's all about the uh, video. If you find a few more frequently asked questions, if you have any questions, you can comment. I try to respond. Thank you for watching.